Hi guys, in this video we are going to learn about the Arrhenius theory of electrolytic dissociation, Debye Huckel theory for strong electrolytes, migration of ions and transport number. Then firstly we will discuss about the Arrhenius theory of electrolytic dissociation. Arrhenius put forth this theory in 1884. The postulates of Arrhenius theory are any molecule of an electrolyte, it splits into the two types of charged particles in any solvent, that is a cation and anion. The total charge present on the cation in the solution is equal but opposite to that present on anion, and the whole solution is neutral. Means if we dissolve any type of an electrolyte in a solvent, then that electrolyte is splits up into two types of charged particles. That positively charged particle is called as the cation and the negatively charged particle is called as the anion. And the total charges of cation and anion in that electrolytic solutions are equal, and therefore the whole solution becomes a neutral in nature. Okay, these ions are constantly reunite to form the undissociated molecules. Suppose a AB electrolyte is added into the water and it is dissociated into the A plus and B minus. This A plus B minus again they reunites to form a corresponding neutral molecule A and B, and therefore that is the neutral and dissociated ions are in equilibrium with each other, and therefore what we call that is these unites, that is ions are constantly reunite to form the undissociated molecule. Okay, the ions are free to move in the solution. This electric current does not produce the ions in the electrolytic solution, but it has a directive effect on the ion already present in the solution. Means in case of the electrolytes in their aqueous solution, that is the ions are already produced, and therefore whatever may be the electric current is there, that is that electric current, it gives a directive effect on the ions which is to be already present in the solution. The properties of the electrolyte in the solution are the properties of the ions produced. Means here in this case, the property, whatever may be the property of electrolyte solution, that property of electrolytes in the solution are nothing but the properties of ions produced. Means ions produced in the electrolytic solution, they give their own properties for that particular electrolytic solution. The electrolytes in the given solution may not be completely ionized. Okay, if we dissolve an electrolyte in a solvent, then it will give the electrolytic solution, and in this case these electrolytes in that solvents may not be completely ionized. Means the fraction of the total molecules gets ionized. Suppose if we have dissolved added 50 molecules of sodium chloride in water, then at that time that 50 molecules of the sodium chloride may not be dissociated into the sodium ions or chloride ions. That is, sodium chloride is the strong electrolyte, it is to be completely dissociated. Okay, means if any type of an electrolyte, when it is to be dissolved in aqueous solution, it may not be completely ionized. Means if we add a particular electrolyte, 50 or 100 molecules of a particular electrolyte, that 50 or 100 molecules of electrolyte may not be completely ionized into the what cations and anions. The fraction of the total molecules gets ionized. Means out of 50, maybe 25, maybe 30 molecules gets ionized, and this is called as electrolytic dissociation, or it is called as the ionization, and this is nothing but the degree of dissociation, or it is called as the degree of ionization. And degree of dissociation and degree of ionization, it is to be denoted with the letter that is alpha, and that is nothing but it is the fraction of the number of molecules dissociated into ions divided by total number of the molecules taken. Means here in this case, fraction of the neutral molecules gets dissociated into ions, it is nothing but the degree of dissociation. The value of this degree of dissociation or ionization, it depends upon certain factors. That the first one is the nature of electrolyte. Here in this case, that is a strong electrolyte gets 100% dissociated. Suppose a sodium chloride is a strong electrolyte and we have taken the 50 molecules of the sodium chloride, and this 50 molecules of sodium chloride gets dissociated into the what? Sodium ions and chloride ions. Means in this case, that is the number of molecules dissociated into ions are 50, and the total number of molecules, neutral molecules taken are 50. Means 50 divided by 50, therefore at that time the alpha is equal to the 1. Means for any strong electrolyte, the value of alpha is equal to the 1. Means the substance which has a degree of ionization or the degree of dissociation that is equal to the 1, all that substances are acts as a strong electrolytes. And for weak electrolytes, the degree of dissociation or the degree of what we call the ionization, it is to be less than 1. Okay, because here in this case, fraction of the molecules get dissociated in case of an weak electrolytes. Then next one is the nature of the solvent. High electric solvent like water are highly ionized, while low dielectric solvents like benzene are weakly ionized. Means that is the alpha is also be depends upon the nature of the solvent, that is it depends upon the high dielectric solvents and low dielectric solvents. Okay, then next one is the presence of other solutes. Okay, that is the presence of other solute also affect the value of alpha of the solute. The presence of same ions from the another solute depresses the degree of ionization of the given solute. Suppose if we have dissolved a silver nitrate in water and we have prepared this electrolytic solution. Again we added the silver chloride into that silver nitrate electrolytic solution. Then this solution has the silver ions as a common ions, and due to that one, that is a degree of ionization of this silver chloride, it is to be depresses due to the presence of the silver ions from the silver nitrate. Okay, therefore this is the one factor which affects the value of alpha. Next one is the dilution. The degree of ionization increases with dilution and it becomes the maximum at very high dilution, and it is called as the at infinite dilution. Okay, this is the another one thing, that means on increasing the dilution, dissociation of the ions is increases. Means a dissociation of ions, it is to be expressed in terms of the degree of ionization, that is the alpha, and it is increases on dilution. Next one is the temperature. The value of alpha increases with increasing the temperature. Means again the dissociation of molecule, it is to be increases with increasing the what? Temperature. Means the factors which affects on the conductance, that is the what we call, that is the which affects the dissociation is the temperature, dilution, again what called the viscosity. Okay, all these things gets decreased with increasing the hot temperature. Interionic interaction, that is solvent solute solute interaction, solute solvent interaction, solvent solvent interaction, all these things gets decreases with increasing the temperature, and therefore what happens, that is the alpha, that is what we call the degree of ionization, it is to be increases with increasing the temperature. The ions behaves like molecules in producing the properties like osmotic pressure, depression in freezing point, elevation in the boiling point, and relative lowering of vapor pressure. There are the certain types of limitations of Arrhenius theory of electrolytic dissociation. Here in this case, although this Arrhenius theory was quite successful in explaining the behavior of weak electrolytes, yet it could not be explain the various observable facts about the strong electrolytes. Okay, some important limitations of Arrhenius theory are: these strong electrolytes conducts electricity in fused states, but it is in contradiction with the Arrhenius theory. According to the Arrhenius theory, that is the formation of ions, it is to be takes place only in the presence of solvent. Means when any electrolyte dissolve in particular solvent, at that time only they forms ions. Means the dissociation of ion is takes place and it conducts the electricity. But in case of an strong electrolytes, that strong electrolytes also conducts electricity in fused state in the absence of solvent also. Okay, means this is the one of the limitation that Arrhenius theory could not explain the conduction of electricity by the strong electrolytes in their fused states. This theory fails to explain the factors affecting the mobility of ions. It explains the factors affecting on the what value of degree of ionization, but it is fails to explain the factors affecting the mobility of ions, that is the speed of the ions. Then Oswald dilution law, which is completely based on the Arrhenius theory, is applicable only for the electrolytes and it fails in case of an strong electrolytes. Means here in this case whatever may be the postulates of the Arrhenius theory, they are applied for the weak electrolytes and it is fails in case of an strong electrolytes. To explain the limitations of the Arrhenius theory, that is of electrolytic dissociation, the various theories were put forward from time to time, but some of these could explain the behavior of strong electrolytes. The accepted theory is the Debye-Huckel theory, was developed in 1923. Later on, this theory, it is to be developed by the Onsager on the basis of interionic concepts. According to this theory, all the electrolytes are completely ionized in all dilution. Means for strong electrolytes, the degree of dissociation is 100%. The ratio of lambda V upon lambda infinity means that is the conductance at dilution V to the conductance at infinite dilution for strong electrolyte does not represent the degree of ionization, but it is the conductivity ratio. Okay, means the dilution, it does not affect the dissociation of strong electrolytes. Means the degree of, means for strong electrolyte, its conductance at V dilution and its conductance at infinite dilution, it remains same. And therefore, whatever may be its conductance at V dilution and its conductance at lambda, that is at infinite dilution, that is what we call the lambda infinity, this ratio is not represent the degree of ionization, but it is just as a conductivity ratio. The increasing the conductivity of strong electrolytes solution on dilution is not due to the increasing the number of ions, or it is not due to the increasing the degree of ions, but it is due to the increasing the speed of ions, or what we call the mobility of ions. But it is not happen in case of an weak electrolytes. In case of an weak electrolytes, that is conduction of electricity on dilution is to be increases due to the increase in the dissociation, means increase in the degree of ionization, as well as increase in the mobility of ions. Two ions present in the solution obey the Coulomb's law. That is, suppose a Q1, Q2 are the two charged particles and R is the distance between them. Then according to the Coulomb's law, that is F, it is equal to Q1, Q2 divided by R square. Each ion is surrounded by the ionic atmosphere of oppositely charged ions. Suppose in a solvent or in an electrolytic solution, both positive and negatively charged ions are present. The positively charged ion is surrounded by the negatively charged ion, and that negatively charged ions are again surrounded by the molecules of the solvents. And therefore, a such type of an atmosphere which is to be created in the electrolytic solution, and that is called as the ionic atmosphere. Suppose here in this case, sodium chloride is the electrolyte, it is dissolved in aqueous solution, and here in this case, it creates an ionic atmosphere in that electrolytic solution. That sodium ions are surrounded by these chloride ions, negatively charged ions, and that negatively charged ions are attached with the what? A solvent molecules, and one atmosphere is created, and it is called as the ionic atmosphere. Similarly, the negative ions are again surrounded by the positive ions, and positive ions are surrounded by the solvent molecules, and vice versa. That thing is called as the ionic atmosphere. Then, in case of this one, this Debye-Huckel theory, it is to be extended by the Onsager equation, Onsager, and therefore they have given a one type of a mathematical equation, and that is called as Debye-Huckel-Onsager equation. In case of a strong electrolytes, the value of conductance at dilution V is much less than the conductance at infinite dilution. Then what is the reason? It is due to the following reasons. The one is the relaxation effect, or it is called as the asymmetric effect. Such type of an ionic atmosphere is there in the electrolytic solution, and this ionic atmosphere, it affects for the mobility of ions. We know that is according to the Debye Huckel theory, that is the conductance of strong electrolytes, it does not affect the dilution. That is the conductance at dilution V and conductance at infinite dilution. That is the degree of dissociation is same, because strong electrolytes are 100% dissociated at any dilution. But whatever may be the conductance, it is to be increases for strong electrolyte on dilution. It is due to the mobility of ions or the speed of ions, and this speed of ions, it is affected due to the ionic atmosphere, and this is to be explained on the basis of this relaxation effect or asymmetric effect. What is the relaxation effect or asymmetric effect? Suppose here in an electrolytic solution, such type of an ionic atmosphere is generated, in which the positively charged is surrounded by the negatively charged ions, and it is attached by the solvent molecules. Due to the interionic force, each ion has a tendency to be surrounded by the ions of oppositely charges, called the ionic atmosphere. Let us suppose a positively charged ion be surrounded by the ionic atmosphere of negatively charged ion. When an EMF is applied, see, to that electrolytic solution, if we apply the EMF, or if we dip the electrodes, that is anode and cathode, into the electrolytic solution, then the positively charged ions move toward the negatively charged electrode, that is cathode, whereas the ionic atmosphere of negatively charged ions is left behind to disperse, while the new ionic atmosphere is under, see here, this is the old ionic atmosphere. When we applied the EMF, the positively charged ion, it is moved towards the oppositely charged electrode cathode, and ionic atmosphere of negatively charged ions, it left behind to disperse, while a new ionic atmosphere is under formation in front of it, but the new ionic atmosphere is not formed at the same rate at which the old disperses, and latter takes more time, and this called the relaxation time. Here in this case, it shows that to form a new atmosphere, When the old ionic atmosphere is dispersed, it takes a certain types of time, and therefore this mobility of ions gets decreases, and this time which is to be required to construct a new ionic atmosphere, it is called as the relaxation effect. Therefore, the ion will always be discharged back or dragged back. The effect thus decreases the mobility of ions and is known as a relaxation effect or asymmetric effect. Then another reason that for strong electrolyte, conduction at V dilution is much more less than the conductance at infinite dilution is the electrophoretic effect. Then what is meant by the electrophoretic effect? Similarly, see here, a such type of an ionic atmosphere is created in the electrolytic solution of strong electrolyte. The solvent molecules are attached to the ionic atmosphere, move in a direction opposite to that of the central ion. See here, when we apply the EMF, this central ion move toward the oppositely charged electrode, and this negatively charged ions left behind, and during this one, the solvent molecules attached to this ionic atmosphere move in the direction opposite to that of the central ion. See here, this solvent molecules, they move opposite to this positively charged ion or the central ion. Thus, they cause the friction due to which mobility of central ion is retarded. Okay, means here in this case, these solvent molecules moves opposite to that of the central ion, and due to that one, the friction is causes between the central ion and this solvent molecules which is attached to this ionic atmosphere, and therefore that is the mobility or the speed of this central ion, it is to be decreases or it is retarded. This effect is called as electrophoretic effect. Okay, means in this case, what we call the solvent molecules attached to the ionic atmosphere moves in the direction opposite to that of the central ions. Due to this, they cause the friction and the mobility of central ion is retarded, and this is called as the electrophoretic effect. Okay, due to these two reasons, the what we call the conductance of strong electrolyte at V dilution is much more less than the conductance at infinite dilution. Means when the dilution it is to be increases, then at that time what happens at infinite dilution, the ions are apart from each other, and therefore the ions are free to move to the oppositely charged electrodes, means a relaxation effect as well as the electrophoretic effect are decreases on dilution, and therefore the electrical conductance of the strong electrolyte increases at infinite dilution. Then next one is the Debye-Huckel-Onsager equation. This Debye-Huckel explain the mathematically the magnitude of asymmetric and electrophoric effect in terms of the factors such as valency of ions, ionic concentration, dielectric constant and viscosity of the medium. Debye Huckel give the mathematical equation in 1923, and that equation which is to be derived by the Debye and Huckel, it is further extended by the Onsager in 1926, and therefore this equation is called as Debye-Huckel-Onsager equation, which gives the mathematically, or which Debye-Huckel-Onsager works out mathematically to determine the magnitude of asymmetric effect and electrophoretic effect. What is the Debye-Huckel-Onsager equation? This Debye-Onsager equation is shown here. In this equation, whatever may be this lambda, lambda is nothing but the equivalent conductance at any concentration. Lambda O, it is nothing but the equivalent conductance at infinite dilution. D is nothing but the dielectric constant of the medium. N is nothing but neta, it is the viscosity of the medium. T is the temperature of the solution, and C is the concentration of the solution. Means that is whatever may be the equivalent conductance at any solution, it depends upon the equivalent conductance at infinite dilution, dielectric constant, it depends upon viscosity of the medium, temperature of the solution, and the concentration of the solution. Where that is dielectric constant D, temperature T, neta, viscosity are the constant. So then it is to be written as, that is the 82.4 divided by Vt, that is half into neta, it is equal to the A, that is 8.20 into 10 raised to 5 divided by under root dt to the raised to the 3 by 2, it is equal to the B. Means for this equation, Onsager equation 1, we have written this factor, this one factor as A, and this one factor as B. Therefore, the equation 1 can be written as, that is the lambda, it is equal to lambda at infinite dilution, means equivalent conductance at infinite dilution, minus A plus B into the lambda O, that is the equivalent conductance at infinite dilution, into under root C. Then see here the verification of Onsager equation. Then how we will verify the Onsager equation? As the Onsager equation, it is to be applied for both equivalent conductance as well as it is for the molar conductance. Suppose we have taken this lambda m, it may be the equivalent conductance or the molar conductance. From this one, we can write this equation for molar conductance as lambda is equal to the lambda, that is equivalent conductance at infinite dilution, molar conductance at infinite dilution minus A plus B molar conductance at infinite dilution into under root C. And this equation, when we match with the straight line equation, that is y is equal to C plus mx, here in this case, this y is nothing but lambda m, C is nothing but lambda mo, that is nothing but the intercept, that is the C is nothing but the intercept in straight line equation. Therefore, what we can write, that is lambda m, for this it is to be written as this x, okay, that is it is nothing but the what we call m is nothing but the a slope, what we call this lambda m. See in this case y is equal to C plus mx. When we match this equation with this one, that is the C is equal to Y is equal to lambda m, C is equal to lambda 1 0, m is equal to minus a plus b, what we call lambda m0, that is nothing but the slope, and x is nothing but the what, under root c. Then if we plot the graph between this lambda m versus this concentration of the electrolytic solution, or if we plot the molar conductance with the concentration C of the electrolytic solution, or we plot the graph the equivalent conductance of an electrolyte with its concentration, what happens? A straight line should be obtained with slope that is equal to, that is minus a plus b lambda m0, and at that time intercept is lambda 0, and experimentally it is found so. Okay, see here we will get, if we plot the equivalent conductance of strong electrolytes versus their concentration, then what happens? We will get the what? Straight lines. Okay, and therefore here in this case what we call the Onsager equation, it is to be verified. The next one is the migration of ions. We know here in this case every ion has a certain types of an speed. Okay, that so we call the electrical conductance or conduction of electricity. It is depends upon the mobility of ions. That is nothing but the what, migration of ions. Then how we will observe the speed of ions? How we will observe the migration of ions, or how we will observe the mobility of ions? To observe the mobility of ions, here in this case we have to carry out one experiment. In that experiment we have to take on, or let us consider a U tube of uniform cross section. This is the U tube which having the uniform cross section. Fill the lower limb of this A, this is the A limb and this is the B limb. Fill this lower limb of this A with gelatin, KCl and phenolphthalein. Now fill the greater portion of the limb B, this greater portion of the limb B with hot 4% solution of gelatin containing few mLs of saturated KCl to make it conducting, and few drops of potassium hydroxide and phenolphthalein indicator. What happens? This do that phenolphthalein indicator in base, that is potassium hydroxide, gives pink color. This is the pink colored portion. Okay. Why it is pink? It is pink due to the what? This potassium hydroxide and phenolphthalein indicator. Okay. This looks pink, and here in this case there is an absence of potassium hydroxide in the lower limb of A, and due to that one it is the colorless. Then fill the 3/4 of the remaining portion of the limb A, see here this one, with hot solution of gelatin, that is the KCl, and the drop of phenolphthalein indicator, and which is to be the colorless. Allow it to cool. When it sets to form the colorless jelly, then fill the remaining portion of limb A, that is the upper portion, with potassium hydroxide solution, and the upper portion of limb B with hydrochloric acid solution. Finally, these solutions to platinize platinum electrodes in such a way that the negative electrode is in contact with potassium hydroxide solution, which is at the upper limb of the A, and this positive electrode, it is in contact with the hydrochloric acid solution, which is in the upper limb of the B. And when on passing the electricity or electric current, the H plus ions move towards the cathode. See here, move towards the negatively charged electrode, while the OH minus ions from potassium hydroxide move towards this anode positively charged electrode. What happens? The H plus ions which are moving from this HCl ions into the limb B, then this pink color of this jelly gets disappear, and this jelly becomes a colorless due to the movement of H plus ions. Similarly, in case of a limb A, as OH minus ions move into the limb A, and that colorless solution gets converted into the what? Pink. Why? It is due to the movement of OH minus ions from this potassium hydroxide solution into the limb A. See here, in this case, on passing the electricity, that is the colorless portion of the limb A converts into the pink portion to the lesser amount than the pink color, which is to be converted into the colorless. This is due to that the H plus ions moves faster toward the cathode than the OH minus ions toward the anode. Means, from this we confirm that every ion has a certain types of an speed. Every ion has a certain types of an mobility, and therefore hence it proves that the different types of ions moves with the different speeds, and from that we have to conclude that a different ion has the different mobility and speed. Then on that basis we have to explore the transport number. Now, what is the transport number? The fraction of the total current carried out by any one of the ionic species is known as the transport number or transference number, or it is called as Hittorf number of the species, and may be denoted by the set of symbols like T plus, T minus, or it is to be denoted with the what Tc or Ta. It indicates that the transport number for cation, that is the C, and transport number of the anion, that is Ta. Suppose if we have taken, we are going to explain the transport number of the anion, that is T minus, it is equal to the current carried by the anion divided by the total current passed through the solution. Transport number of cation, it is denoted with the T plus, and it is nothing but the fraction of the current carried out by the cation. it is denoted as the current carried by the cation divided by the total current passed through the solution. Means the fraction of the total current carried out the anion, it is called as transport number of the anion, and the fraction of the total current carried out by the cation, it is called as the fraction, that is transport number of cation. The amount of electricity carried out by the anion, it is proportional to the speed of the anion. Okay, that is the speed of ion, it is to be shown with the mu A. And amount of electricity carried out by the cation, it is also proportional to the speed of the cations. Means it shows that is the current carried out by the particular ion, it depends upon the mobility or the speed of the ion. And therefore, mathematically, this transport number of this anion, it is nothing but the speed of the anion, because it is nothing but the current carried out by the anion, it is proportional to the speed of the anion. Therefore, we have to write here that is the transport number of anion, it is equal to the speed of the anion divided by that is the speed of the both, sum of the speed of the both anion and cation. Similarly, speed of, that is transport number of this cation, it is equal to the speed of the cation divided by sum of the speed of the cation as well as the anion. And therefore, if we have to make the total current carried out by the cation and anion, that is the transport number of cation plus transport number of anion, it is equal to, that is this mu A divided by mu A plus mu C divided by mu C plus mu A. Then that is equal to, written as, or above equation it is to be written as mu A plus mu C divided by mu A plus mu C, means that is the total speed of the cation and anion divided by the total speed of the cation and anion, and that is nothing but the 1. And therefore, what we call that is the sum of the transport numbers of the cation and anion, it is equal to the 1. If we know the transport number of any ion, then we have to calculate the transport number of another ion. Suppose if we know the transport number of cation, we can calculate the transport number of anion and vice versa. And here in this case, this is about the transport number. And thank you. Here in this case, if you like this video, please like and subscribe to see the more videos. Thank you.